Okay, so page 1 of our forces packet is vector addition. And so forces is a vector, velocity is a vector, acceleration is a vector. Our first example is going to be distance, no, displacement. Displacement is a vector. And so what we do here isn't just forces, isn't just kinematics. You can do it with anything that's a vector, okay? Later on, we'll be talking about momentum. That's a vector. And so we'll see vectors all year long, okay? Rotation has some vectors to it. And not that we do exactly this same process, but the spirit of vectors and what's true about vectors, magnitude, direction, how we combine vectors, that stuff is going to be true no matter the topic. Good deal? Okay, and so today, if we're lucky, we'll get through page 1. I know that you're like, what? There's 40 pages. Just page 1? Yeah, if we're lucky, okay? There's a lot of little nitty-gritty details with vectors, okay, that I'm going to point out along the way. And so, let me switch over just for a second. An airplane trip, or if you hate airplanes, a train trip, a car trip. Maybe you're walking. That part doesn't matter, okay? We've got 3 legs or 3 parts to the trip with 2 stopovers, 2 pit stops, right? The first leg is due east. East. Okay, so we've got a quadrant system here, an XY chart. Let's go on and identify our compass directions relative to this page, whether it's an actual page or a computer page. And so where does your, XY, where does it all begin? What's the kind of standard 0 point, starting point? 0 degrees. Where's 0 degrees on this? Not really the center. Up, down, left, right. Right. Isn't 0 degrees right here? Isn't that 0 degrees? Standard? In your quadrant, 1, 2, 3, 4? Oh, you're looking that way. That way. It's the only way I know. So, oh, no, not angle between these, sorry. The angle like as a reference point. There we go, okay? And so this 0 degrees, you could also call positive X, right? It's the positive X direction. We know it is to the right. That's what we've mainly been focused on. Well, what if I put a compass direction to it? East, okay? And then we move through quadrant 1 and we go to 90 degrees, which is also known as the y-axis. Is this one positive or negative? Positive. And what compass direction would you give this upward direction? North. Okay. And then go 90 more degrees. And here we are at negative X, or also known as 180. What compass direction would to the left be? West. And then one more. We got 90 more degrees. So 180 plus 90 is 270. And that's also known as negative Y. And what compass direction is remaining? South. Okay, or down the page, right? Okay, so sometimes we're told left, right. Sometimes we're told, an angle, go this angle from, or we might be given compass directions. And so you kind of got to be ready for any of it, okay? And so our first leg, our first vector is due east. And we travel 620 kilometers. Now, kilometers, everybody's kilometers. I know it's not SI unit, but that's okay, because if everybody's in kilometers, I can do vector addition. If I had someone in kilometers, someone in meters, I'd have to do a conversion. And if maybe somebody was in kilometers and then another was in newtons, which is going to be our new force unit, I cannot add a kilometer in newton. That's apples and avocados, okay? They are not the same unit. They're not the same unit for the same quantity, right? And so when you add vectors, it's got to be apples and apples. Or avocados and avocados, right? They have to be not only the same, order of power 10, they got to be for the same quantity. Good deal? Now, some of you have already looked ahead and you're like, but that says Vx and Vy, that's velocity. Actually, no. The V here is a capital V. I know, quit rolling your eyes. It's representing a vector. So what we're about to do in terms of before we plug and chug, before we get answers, the setup is going to be for any vector, okay? Any vector. So when I draw, due east, 620 kilometers, and if you look ahead, that's the biggest number. 620, 440, 550. So this first one is going to be my biggest vector. And so they don't tell me where the trip starts. I'm just going to start at the origin because that's a nice place to start on day one, right? And so I'm going to come here and I'm just going to tell myself this is my initial position. And I'm going to travel. Actually, that's too long for my liking. Not necessarily 6 boxes, but sure, 6 boxes. That's okay. This drawing is not going to be drawn to scale, by the way. But we're going to keep with big, medium, large. No, big, medium, small, right? Relative magnitude. Now hold up, Miss Earhart. You haven't drawn a vector, but I'm doing what a lot of students are going to draw on our exam, on the AP exam. Guess what? If you draw a line for a vector, no points for you. What do you have to draw to make it a vector? An arrow. An arrow shows direction. And so guess what? We're going to grade you for the arrow. Today, when I walk around while you work on question 2, some of you are just going to draw lines and I'm going to take my pen and I'm going to correct it. I'm going to correct it on day 1, right? Let's practice good habits, vectors, magnitude, and direction. Did anyone else watch Despicable Me this weekend or is it just me? We literally did. My son, he's like, I want to watch Despicable Me. And of course, there's a character, Vector, and he makes a big deal about magnitude and direction. It's a little proud moment that there's some accuracy in a cartoon. But anyway, so there's our V1, vector 1. That's going to be my biggest arrow. Now, if this is a road trip, plane trip, whatever, am I going to turn around and go back to the origin before I do the second trip? No, we pull off at a gas station, we go, pick up a bag of chips and a Coke, and then we get back in the car and we keep going. We're going to start vector 2 at the end of vector 1, and I'm going to switch colors. The second leg, the second leg is southeast for 440 kilometers. So same unit, all good. 440 is the smallest number. This is going to be my smallest arrow. Where's southeast? Right and down. There you go. Okay. English is hard sometimes, right? Is it Monday? Okay. Now, I don't go back to the start. I'm already in between quadrant 1 and 4. So how do we do this? Look, watch what I do. Just imagine or literally draw a smaller quadrant at the end of vector 1 to give you a little guidance. You don't have to do this, but we want to draw a small arrow southeast, and that's going to be my vector 2. Now, I'm going to get a little detailed here. Southeast could be drawn like I have it, or it could be a little more south-southeast, southeast-east. There's a lot of variation of southeast, right? Notice in the next vector, they get detailed, 37 degrees, but vector 2 was not detailed. So if they don't tell you, if they just say southeast, we'll assume it's at 45 degrees in that southeast quadrant, quadrant 4, okay? And so you could go on and label that angle there, if you can squeeze it in. I know it's a small arrow. By the way, I'll be redrawing vector 2 later when we need to do a little bit more with it, I don't like my drawings to get too cluttered. So we take another pit stop, right? We fill the car up with gas or whatever. Now, vector 3, and I'm going to switch colors. The third leg is 37 degrees. Notice they don't just say southwest. They say west of south. Tomorrow it might be south of west. So what's the difference? Well, let's draw a little sketch here. It's quadrant 3, right? So quadrant 3, west of south. Let's reword that. Couldn't you say it's to the left of negative y? We said south is negative y, west is to the left. And so the correct way to draw this would be somewhere like this, with 37 degrees touching the negative y-axis, right? So this one is west of south. But the alternate, maybe tomorrow they say south of west. Well, if it's south, below, or underneath of west, that's negative x. Maybe this is south of west. Now you're like, well, no big deal. Another analogy I like to use with vectors, what about a treasure hunt? What if these legs are directions to go find the treasure? This last leg, does that final angle and nitty gritty west of south, south of west, does that make a difference where the treasure is? Yeah, you got two people digging in both spots, only one gets the treasure. And so it is a big deal. It is a difference. Do you see the difference? Yes.
What is the practical application of writing it that way?
Practical, it's just a version. You could also see it left of negative y. They could also, here's another thing they could do. So this is a side note, but we said this is 37 degrees. That's what we decided was correct. They could subtract it from 270 type and give you a big angle. Now that's the alternate. I don't know what math teaches. Maybe they teach both ways. I don't teach the big angle reference because students are like, how do you have a right triangle with 220 whatever degrees? The angles add up to 180 in a right triangle. So whenever you say, oh, we have a 220 degree angle, they're like, how do I draw the triangle for that? And so I tend to keep with the smaller angles and just know where it is. Does that help? Okay. So other method is the big angle method. I can teach it to you if you want, but I'm not going to whole class teach it because it tends to confuse more than not. So now that we know how to draw it correctly, I'm going to switch back to green. We know it should be to the left of south. And again, just draw yourself a little axis here for reference. And this 550 is going to be kind of our medium length arrow. And so we want to be closer to the south, we said. And so there's our 37 degrees, and this is vector 3. Actually, I'm going to move that. I'm going to label down below. So there's our vector 3. Now, kind of go with that treasure hunt. If everybody is doing step 1, step 2, step 3, maybe I'm a little smarter and I do a little vector addition and I can find the shortcut so I get to the treasure first, right? Notice this is where we end, right? Whatever spot we end with is your final position. The question up above says, what's the object's plane's total displacement? Well, what is displacement? It's the distance from the starting point, and you don't ignore direction, right? And so it's that final minus initial as an equation. But I've got 2 points labeled xi, xf. The shortest distance between 2 points is a straight line, or in our case, as a vector, a straight arrow. And I want to use a 4th color. And so this is your displacement, since we're dealing with distances here and positions, right? However, in the generic sense, this vector is not going to be labeled V4, VR. And you're like, what's R? So here's a new vocab word, okay? This is the resultant. This is the one vector that takes the place of those three that get you to the same spot. It's the shortcut. You want the treasure? Find the shortcut, right? Okay, so you can start digging in the right place. Now, notice my arrowhead. Okay, let's talk arrowheads. The first three, we picked up where we left off, right? And so V1, V2, and V3 were the individual vectors. We drew them with a method called tip to tail. And you're like, Mr. Hart, you made that up. That's so silly. I did not make it up. It's a legitimate physics kind of term or process, although some textbooks call it head to tail. That's no big deal, right? An arrowhead, okay? But tip to tail, at the tip of the first arrow, you put the tail of the second. We pick up where we left off. However, when you look at the resultant vector, so the resultant, or what I labeled VR, and again, these V's are vector, not velocity. How did I draw the vector for the resultant? Yeah, that's kind of awkward. It's not tip to tail, just note to self. It does not cycle back, but I drew it from XI to XF. I drew it from start to finish. How about that? It's the shortcut. It's an alternate to the three legs. Do you actually do 4 legs? No. You either do 3 the long scenic route or you do 1 shortcut. That's your options here. So they both start at the same place and they end at the same place. It's just one takes more time, more distance to cover than the shortcut. Yes. Yeah, you can do velocity vectors. Yeah, good question. So vector is usually a capital V. And I will tell you, I'm a little lazy on this. I'm a little lazy. It's not a habit of mine, but technically you read your book and such, and vectors have what's called vector notation. Now this isn't going to answer how do you know if it's velocity, because velocity is a vector. It's got a arrow on it, right? But usually vector in a generic sense is a capital V. And thank goodness we're not studying electricity, because capital V also stands for voltage. That's next year. Okay. I don't know. I'll think about that later. Okay. So there's your terminology. We've got individual vectors. The independent ones are added tip to tail, pick up where we left off. That's all it is. But your resultant vector, start to finish. It does not cycle back. And I emphasize that on the AP exam, I bet you a burrito that there's a multiple choice question with a bunch of arrows drawn. Yeah, burrito, okay? There's a bunch of arrows drawn, right? And you have to pick out who's drawn correctly. One of those answer choices is gonna have the resultant pointed towards the origin, pointed towards where you started. It's gonna look like a cyclic, right? And I bet half the nation picks that one as the answer choice. It's wrong, okay? The resultant is from start to finish. Don't miss that problem, okay? Okay, so now we've got a sketch drawn. Now sketches, they're not a requirement. In fact, it's not drawn to scale. So I'm gonna put that note, just so you know, not drawn to scale. The only way to draw it to scale is with a protractor to get those angles right? But guess what a forbidden item is, a prohibited item on the May exam? Protractor. You can only have a ruler. You can't have a protractor. So how are we going to do this accurate if we can't have a protractor? Trig. We got angles. We need components. And so now let's do the accuracy portion of this, right? We kind of know where it should be pointed southeastish towards quadrant 1, right? And so we know something about the resultant, which is the displacement that we're trying to get. By the way, final answer is going to be magnitude, which means what? The size, the number, the value of your final displacement. And so it's the magnitude of the resultant vector is really what they're going for here. On this problem, it's displacement. And then direction, southeast, too generic, not find the treasure. What do we really want for the direction, the degree, the angle, okay? And so usually you find the angle from your starting, okay? So from where you started. Nearest axis, there's multiple ways to do it. If I find the angle with the x-axis, you can find it with the vertical. There's usually, complementary angles there. And so before we can get those answers, can I add all these distances, 620, 440, and 550? Just add them together. That's our answer. False. What would that give you? Distance. They ask for displacement. You have to take direction into account. Well, some of these move in the horizontal, some move vertical. Just like we did with launch speed and impact speed, we break each vector up into components. And so this is the horizontal components, right? And then we have the sum. Sigma means sum, right? We saw that previously. You'll see that sigma sign a lot. Not that you have to know Greek. You just have to know what to do. It means you sum the vectors in the horizontal. And then separately, we sum the vertical components. Okay. So I have 3 vectors. So again, I'm going to go generic to start. Well, vector 1, I would have v1x, and then down below, v1y. So previously in projectiles, we made an XY table. You could do that as well. Here, we're going to do it more of a statement form. And then same thing, we're summing v2x, and then down below, v2y. And then we have 3 total, so I need 3 total components in each one. But notice you keep the x components with the x components and the y components with the y components. Just like we learned in projectiles, the x and y direction are independent of each other. You cannot add x with y, but you can add x with x and y with y. Everybody good there? And then fast forward, later we'll get a number here. Then what are these? Sum of Vx and sum of Vy. Well, these together are going to be the components of the resultant vector. Resultant vector. Once you know the components of the resultant, how do I find the magnitude of the resultant? Think back to impact speed. I'm going to slide over. Y'all remember projectiles, right? And whenever it landed, we said, what's the impact speed? Well, it was at an angle, so we had to know the y component and the x component. Pythagorean. And so all of this vector addition ends with Pythagorean theorem. And then how do you find the direction? If you know all sides of your final resultant, pick your favorite SOHCAHTOA, right? Textbooks are going to use inverse tan. I'll be using inverse tan. But true story, if you know the hypotenuse, the resultant, you can use any of them. So that's just kind of the game plan before we do numbers, okay? And so each vector has 2 components. Separate your horizontal, sum them, and then sum the vertical. And then you'll have the components for the resultant Pythagorean inverse tan. Again, this is very procedural, okay? Questions before we start doing numbers? All right, well, starting with the red. Red was 620 kilometers due east. Was it northeast, southeast? No, it's just east. Is there any vertical anything with due east? No, the red one, V1, did not go up or down. So this one's easy. The vertical component for the first vector is 0, which means all 620 is in the horizontal. And it was east, that's positive x, so it's going to be a positive 620. Because your due east is a straight to the right. There's no up and right or down and right. There's no north and south with it. So there's literally no vertical component. So it's all in the horizontal. And then second vector, I'm going to go back to the picture. It had that 45 degrees, we assumed, because it just said southeast, no angle reference, so dead center, 45 degrees. Now I'm going to redraw that so I can do a little bit of more work with it. So this is V2. And we said it's at a 45-degree angle in quadrant 4. You could put it on the other side too, either way. Well, that southeast has an eastward component and a southward component. And so V2 is 440 kilometers. How am I going to find the horizontal component of that 440? Notice the x component is adjacent. 440 is your hypotenuse. So we'll use which SOHCAHTOA? Cosine. And so cosine 45 would equal that V2x over 440. And so grab a calculator, make sure you're in degree mode. It matters. This one's in radians, so don't ever assume. Always check. And so we multiply both sides by 440, and I get 311. Yes, there's a decimal, 0.12. I'm just going to drop it. And so 311, and it would still be kilometers, okay? So again, apples, apples, avocados, avocados. If I have a hypotenuse in kilometers, all my components are kilometers, okay? And so that's V2x. Now it's eastward. Is that positive or negative? East is positive, so it should be a positive 311. And you're like, well, duh, Miss Earhart, the calculator told me. Hold that thought. Let's do the y component. Well, 45 degrees is special, right? So sine 45, or I'm sorry, this is opposite. So to use sine 45, it'll turn out to be the same value, right? So that's the beauty of 45 degrees. The components are equal. So we know it's 311, but wait, there's more. What direction is this vertical component? It's south, it's negative. Why? The calculator didn't tell me so, but I know more physics than the calculator, right? Hopefully. And so here, I'll add a negative 311. Okay, or just start your subtraction. Same difference. Good there? Oh, I should have wrote that in blue. I always do my best to color coordinate. Okay. Vector 3, going back to the picture, turning on my green. This is the one that was 37 degrees west of south, right? Now I'm going to draw that triangle. And again, there's a couple ways you can draw it. But here's what I had started. Let's solve for the x. What function are we going to use for the x component? Oh, I'm so glad you said that. I was expecting at least 3 people to go cosine, 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 because Miss Earhart, all the time, we use cosine to find the x component. And I would have said, well, remember back in the day with 2D, I said most of the time you do that. I said, we'll get to when you don't. Here's where we don't. The x component is not adjacent to 37 degrees. It's actually the opposite. And the 550 kilometers they gave us would be the hypotenuse. And so to find the x component here, since the angle touches a vertical axis, we'll use sine. And so sine 37 is going to give us v3x over the hypotenuse 550. And so multiply both sides by 550, and I get 331. Careful, 311, 331, careful. I already made that mistake, okay? But wait, there's more. It's west. What do we know about west? Negative. Got to make that negative. And so I'm going to go back up to my x statement and say plus a negative or minus 331. Now, yes, I'll do the math there, but hold on. We still got a y component. It is not going to be equal because it's not 45 degrees. Now, how do I find the y component? Which is adjacent to 37 degrees. Cosine. Now, true story. We know 2 sides. You could do Pythagorean. You could do tan. But textbooks are going to use cosine here. Okay, so just saying. So cosine 37 would equal that v3y over 550. So a quick lesson from vector 3, don't always use cosine for x and sine for y, because that's only if the angle touches the horizontal axis. You do the opposite if it touches the opposite axis. And so 550 times cosine 37, I get 439. But wait, there's more. What direction is this y component going? Negative. So I got to make sure that for quadrant 3, both components get a negative, right? So to me, it's helpful to do the drawing so I see the actual direction. Sometimes the words don't convey the full message for some. Pictures help. If it helps when I draw pictures, then I highly recommend here in the beginning, you start with drawing your pictures. Even I redrew vector 2 and 3 just to make it a little bigger. I say I'm zooming in, right? I'm just drawing it a little bigger so I can work with it. All right, now we know all the individual components. I can add all the horizontal components together, bless you, and get the sum of the horizontal components, and I can add all the verticals together and sum the vertical vector components. And so I got 439, notice it's negative, just like negative 311. So we're going to sum those 2 numbers plus 0, and I get a negative 750. Kilometer, kilometer, kilometer. My answer is going to be kilometer here. And then same-ish thing with the horizontal. Be careful with that 311, 331. And I get a positive 600 kilometers. Everybody good there? Now, earlier I said, what did we just find? We just found the components of the resultant vector. I'm going to redraw. Actually, I can go back to my original drawing. No, I can't. It's already cluttered enough. I'm going to redraw those 2. And so these 2 components, I'm going to say, and it doesn't matter which one you start with. I usually just tend to start with the horizontal. And so I'm going to have a positive 600 kilometers for my sum of Vx. Tip to tail, I'm going to go south a little bit bigger for my sum of vertical that's negative 750 kilometers. So we just found the components of our vector sum, our resultant vector. Then, so I could do these two steps to go find the treasure, but again, the straightest distance, no, the straightest point between 2 points, no. Yeah, the shortest distance, I was right, the shortest distance between 2 points is a straight line. And so start to finish, okay, it's not cyclic. This is our resultant vector. And so how do I get the magnitude of that number? Pythagorean theorem. So do your squares. Notice negative 750 squared is going to square away. It's going to turn positive. Save a keystroke. Don't even put it in. Because if you don't put it in parentheses, the calculator misinterprets. It'll subtract. We don't want that. And then square root that final answer. I get the magnitude of VR to be 960 kilometers. So that's one part of my final answer. The treasure is 960 kilometers away. But at what direction? Don't just say southeast. You won't find the treasure. What do we need? The degree, the angle. Now, based on my drawing, I said it's the angle from the start point, right? So I'm going to label this as the angle of my resultant, theta r. And again, inverse tan. So inverse tan, second button, shift button, tan, right? And then opposite is the 750 divided by 600. And if you're wondering, why'd you leave the negative off? If you remember, tan gets confused. It doesn't know if you're in quadrant 4 or quadrant 2. It'll just know one of them's negative, right? And so just magnitude. We redrew it. We know where it is. It's in quadrant 4, right? We know the angle that we're looking for is there. So just 750 divided by 600, inverse tan that, and I get 51 degrees. So the treasure is 960 kilometers at 51 degrees. And everybody's headed to what quadrant? If I tell you 51 degrees, pretty much everybody's going for quadrant 1. If I hadn't redrawn that picture, right? They're going for quadrant 1. Are they going to find the treasure? No, so let's be more specific. It's 51 degrees below the positive x-axis. Or you could say 51 degrees south of east. Just giving you both. Or if you're like, well, it's 51 degrees from 360, couldn't I just say negative 51? If you go the other direction, you could report the negative angle. I'll tell you that's not very common, like with textbook answers, okay? Or you could say, 360 minus the 51, or you could say 309 degrees. And again, you're like, but that's not a right triangle. I know, it's the big angle reference. It's more of like a reference point. Everybody would agree 309 is in quadrant 4, right? Either way, I tend to stick with, here's my magnitude, and then I'm okay with compass directions. But you could also say below positive x. Everybody good? Okay, ask me a question. That was a lot, right? So actually think of your question. Let me kind of recap what we did. We took our 3 individual vectors, did a qualitative sketch to get an idea where it should be. But for accuracy, we broke each individual vector into horizontal, vertical components. Then we summed the horizontals and we summed the verticals separately to get the components of our final resultant answer. And once I knew those, then I could do Pythagorean to get the actual magnitude of the resultant. And then we did an inverse trig function, tan today, cosine sine tomorrow is fine, to get the angle and we were very detailed where that angle was. Okay, now ask me your questions. Maybe you don't know what questions you have until you try one yourself. And so now the rest of this class, we got about 20-ish minutes. I want you to try the one down below. Now, let me show you a couple differences, because no two problems in physics are identical, right? Have we learned that? Okay. I don't see kilometers, I see N, but those arrows aren't pointed north. That's right. The N stands for our new unit coming your way next class, Newton. It's for forces. And so, and notice the picture. Uh-oh, did they do the tip to tail method? No, they did tail to tail. Now you'll see me do a couple tail to tail. There's a reason for it. So this isn't uncommon with forces, but it's kind of hard to tell your resultant when they're not drawn properly. So that's the blank grid line there. If you want to do the sketch, you don't have to. Your accuracy comes from the trig, right? And so at the end of the day, these two forces are acting on one object. Maybe it's two people fighting over a toy, if you're my two kids. Get the magnitude and the direction that's of your one resultant answer, same steps. And to get it, you probably want to sum the x and y components. Two vectors, two components each. Good deal? All right, so give that one a try. I'll be walking around to answer your questions, ask each other questions, work together. Hopefully you can get this one done before you leave. All right, we're only going to spend like 15-ish minutes next class on vector addition, and then we're jumping right into forces.